Welcome, folks. A video on an introduction to linear algebra. What is linear algebra? In this video, we'll discuss briefly a little bit of what makes linear algebra linear and what makes linear algebra algebra. And then we'll see a motivating example through an application. So for now, we can think about linear algebra as being flat. So you might know things that are linear from pre-calculus, things like lines, or if you're lucky enough to have had a little bit of multivariable calculus, you might know about planes. Those are examples of things that are flat, linear. In general, however, this class won't have too much interest in geometric interpretation, but in any case, we can think about things that are flat. Equation-wise, we think about things that are linear. It's sort of easier to talk about things that are not linear. So these examples on the bottom are examples of things that are not linear because they include products, squares, tangents, logarithms, and things of that nature. So all of these things are examples of things that are not linear because of those various products or logarithms or tangents, so on and so forth. The equations above are examples of equations that are linear. And the key here is that each unknown variable, whether it's x, y, and z, whether it's x1 through x5, or whether it's a, b, c, and d, that those variables only appear once and there are no products times anything else. So we'll see an example of how to write a system of linear equations and how to identify linearity. But for the time being, it's a little bit easier to think about linear in terms of things that are not linear. So the lower half is not linear, and we see that we see why. Okay, by algebra, however, we just mean expanding arithmetic. So in this class, we'll use arithmetic of real values as well as arithmetic of complex numbers. So just a couple quick examples. For instance, if x is 2 and y is 3, we can quickly compute 3x plus 7y. Okay, so a pretty straightforward operation here. 3 times 2 plus 7 times 3 gives us 6 plus 21, which is 27. We can also do more complicated calculations too, like this one, x plus y minus 2xy. So we see here that x plus y quantity squared minus 2xy gives us 13. It's also going to be important for us to be able to do complex arithmetic. So we see here that we can compute, for instance, 2 times z1 plus 3 times z2, for z1 is 3 plus I, and z2 is 3 minus I. So we see here that complex arithmetic gives us the value of 15 minus I when we collect up the real and the imaginary parts of this complex number. We can also do complex computations with products, and it helps to keep in mind just that I squared is minus 1. In this case, the value we get by multiplying these complex numbers is 4. Okay, a brief discussion of an application here. We're going to assume that you're in charge of cooking up some trail mix, and the trail mix is made with raisins and peanuts and chocolate. And we're going to assume that in storage we have a certain amount of raisins, peanuts, and chocolate. And we're going to assume that we construct different types of trail mix based on the ingredients, right? So you might not be surprised to see here that the fancy mix has more chocolate and less raisins, whereas the bulk mix has more raisins and peanuts and less chocolate. Okay, so something we can do here is cook up some equations for 15 kilogram batches based on these ingredient ratios. So in order to do that, we'll just go ahead and write a system of equations here. So here's the first equation. The first equation describes the total amount of raisins used, right? So 7 kilograms out of every 15 kilogram bulk batch is raisins, 6 kilograms out of every 15 kilogram batch of the standard mix is raisins, and 2 kilograms out of every 15 kilogram batch of the fancy mix is raisins. So we see that those ratios give us this total amount, right, of 380 kilograms used. And then similarly, for the total amount of peanuts and the total amount of chocolate, we can cook up equations for those. Okay, so here's an opportunity for you to work something out on your own. And when we have these worksheet items, it refers back to an activity that we'll discuss in class. So check out Canvas for the associated worksheet, but we'll verify that 300 kilograms of bulk, 300 kilograms of standard, and 300 kilograms of fancy is a solution to this system of linear equations. And the way that we'll do that is by substituting in those numbers for B, S, and F, and showing that each equation is simultaneously satisfied. So I'll go ahead and just illustrate the first one, and then I'll leave it to you to do the other two. So we see that when B is 300, S is 300, and F is 900, that this sort of simple linear calculation gives us 380. So we see that the ratio of raisins is satisfied in each batch. And the same thing is true for the equation for peanuts and chocolate as well. Now, something else you might want to do is compute the daily profit for a sale of this amount of bulk, standard, and fancy. And this also is sort of an example of a pretty straightforward linear calculation. So we see that we can express the profit as the amount of bulk sold times the net gain for selling the bulk, which is the sale price minus the cost, plus the amount of standard sold times the net price, times the amount of fancy sold times its net price. So again, an example of a linear calculation, and we end up with $2,727. And this is per day, so we'll use the units of per day. Now, things are wont to change, as they likely do, and one change might be changing a new mixing scheme here, where we change the amount of bulk, fancy, and standard, and change the proportions in each batch. So we can sort of play the same game here and find new equations for the total amount of each ingredient consumed daily. So here's the equation that tells us the ratios of peanuts, and we can see how to find this is the equation for the raisins. We can see how to find equations for the peanuts and the chocolate similarly. So proceeding similarly, we see that a system of equations ends up being these three equations in these three unknown variables: bulk, standard, and fancy. Now it turns out that, unlike before, and I didn't mention this, but it turns out the system before, the solution that we illustrated as the only solution, it turns out that this system has a different characteristic, in that if we arrange the amount of bulk and the amount of standard to depend on the amount of fancy, these amounts of bulk and standard satisfy each equation independent of the amount of fancy. So I'll go ahead and sort of illustrate this the same way by just substituting these values for bulk and standard into the equation, simplifying and showing that the equation is satisfied. So here I'll omit some of the algebraic details, but when we substitute the given amount of bulk and the given amount of standard into our equation, we can see that the fancy adds to 0 and the constants add to a number that when divided by 15 gives you 380. So the first equation is satisfied. And it turns out this is true for the second equation and the third equation too. Now, I want to point out that an important feature of this system is that our bulk, standard, and fancy amounts are non-negative, right? It wouldn't make sense to have a negative amount of stuff. So we'll go ahead and apply that restriction that we have positive amounts of stuff and see what that means. In this case, the requirement that the amount of bulk be non-negative implies that the amount of fancy is greater than 825 kilograms. And similarly, the requirement that the amount of standard be non-negative implies that the amount of fancy has to be less than or equal to 960 kilograms. So it turns out here that we have sort of a range of fancy, but these values of bulk and standard will work for any value of fancy in that range. I'll let you check this out on the worksheet. Now we can go ahead and compute the profit in this case too, and we'll do this the same way we did before. And we see that there's sort of a slightly different pricing scheme here too, because we changed the amounts. So in this case, we see that the profit is a function of the amount of fancy, and keeping in mind here that the amount of fancy ranges between 825 and 960, we can see that in order to maximize the profit, we might consider using the least amount of fancy as possible, right? So the max profit, because of this negative coefficient on the F here, is when the amount of fancy is 825. In this case, it turns out that using that amount of fancy at 825 gives us a profit of $2,805 per day. Now, it also has the interesting feature that we end up using 0 bulk and 675 kilograms of standard in this scheme. And we find those amounts of bulk and standard just by substituting this amount of fancy, 875, into those equations for bulk and standard. Now, one thing we could consider is changing the pricing scheme. And here we'll change the sale price of standard from $5.50 to a different number. We'll change that number to $5.25. We can play the same game here and compute a profit based on this new pricing scheme. It's a similar linear calculation, and I won't go through it in its detail. So in this case, it turns out that that profit function, which is a function of fancy, is 0.21 times the amount of fancy plus 2,463. Now you might imagine, in order to maximize profit in this case, with a positive coefficient here for the amount of fancy, we'll want to choose as much fancy as possible. With this new pricing scheme, choosing 960 kilograms for fancy to get the max profit, it turns out that we use 0 standard and 540 kilograms of bulk for a profit of $2,664.60. I'll mention, although this isn't a part of this course, this is an example of linear programming, which is linear programming is a super interesting and exciting study. I'll also mention that as part of the worksheet, you'll go ahead and have a look at a pricing scheme that gives us the same profit independent of the amount of fancy we look at. So be ready for that and think about that for class. Okay, that's all for this section on an introduction to what is linear algebra. Have a great day, folks, and we'll see you next time.